Thank you. Yeah, I'm happy to keep the ball rolling on this session around non-local computation and tell you more about this connection between position-based cryptography and Hamiltonian simulation. And this is joint work with Toby, Patrick, Tamara, and David, and Toby and Tamara are here. So if you want any questions, you can bug them. Great. So a quick recap of the background, since the topics introduced before involving non-local computation and position-based verification are very relevant for this work. So we're looking at position-based quantum cryptography, which is this idea that the verifiers can use the honest prover's position in space-time as its credential, like how you'd hand your credit card over to someone if they're in a bank, but if you meet the same person on the streets at 3 a.m., maybe not. So more explicitly, you can consider a referee that's split into two sections, each holding half of a bipartite state. They send this in. If the honest prover is in the allotted space-time region, they can perform this computation locally on both halves of the state and then send them back to the verifier at a later time. However, you can spoof these verifiers if there are some attackers that are positioned outside of this local region, and they're allowed to do local computation, maybe some classical communication, and importantly, share some pre-shared entanglement. And the security of these protocols then come down to how much pre-shared entanglement these attackers have to have if they want to spoof the verifiers into convincing them they're in this position. And this is a nice topic to study because there's a big gap of things we don't know. So as Philip mentioned, if we know we have exponential amount of entanglement, then we can always spoof these verifiers. However, the lower bound is only linear. So we're not sure whether position-based cryptography is really secure or maybe not. Maybe there are hints that it is secure, since there are some lower bounds that match the upper bounds, exponential, if you have some limits on the protocol that to do with the unitary. But in general, this is a wide open question. It's exciting to see what we can do. Which is why it was cool when this idea came from holography out of Stanford, that you could think about position-based cryptography and build a attack from ADS-CFT. So you can set up this non-local protocol where the verifier sits on the boundary. And in the bulk, you can do your honest implementation of the unitary. And this unitary sits somewhere deep in the bulk. Whereas on the boundary, there's no intersection of these light cones. So the boundary must be doing this computation non-locally. But since this is a duality, like the ADS-CFT duality, if it's happening in the bulk, then the success also has to happen on the boundary, which means that we get an attack on position-based cryptography by looking at the boundary dual of some unitary that happens deep in ADS. But obviously, this is maybe a few steps short of a practical implementation, things that Philip mentioned earlier. Some being that it relies on being able to do some unitary deep in the bulk of ADS, and also it requires knowing things about this holographic dictionary. So in order to ask questions about whether we can use this nice idea to construct a more practical attack, we turned to the tensor network models of ADS-CFT. So in these tensor network models, we take some space-like slice of ADS, fill it with a tensor network, and use this to map the Hamiltonian, or the state in the bulk, out to the boundary, and then time evolve. And in order to use these models to implement these attacks, it's really essential that the boundary causality is obeyed. So we're promised in ADS-CFT that we have nice straight light cones following the speed of light. And this means that there's no local position on the boundary. And therefore, we're promised that this boundary is doing this computation really non-locally and is giving us an attack. And we know that there exists some tensor network toy models where we have a local boundary Hamiltonian. And you might ask, as we did, is this enough to recover these nice straight light cones and some consistent bulk boundary causality in a way that will give us a nice rigorous recreation of the ideas from ADS-CFT? And to spoil the punchline a little bit, so far the answer has been no. This isn't enough. But Investigating this topic has led us to this nice connection to Hamiltonian simulation and has also helped us improve toy models. So for the rest of my time, I want to talk about a new ingredient that we've added into tensor network toy models that have allowed us to recover some consistent causality on the boundary. And then in the second half, look at how these two toy models allow us to investigate this question of attacks on position-based cryptography from holography and what we can learn there. Okay, so this is my holographic tensor network where I've taken some space-like slice of ADS and tessellated it with some hyperbolic tessellation. In each cell of the tessellation, we've placed some tensor, contracting the legs with the neighboring cells. And each tensor also has an additional leg that's been left dangling, which we can associate with the bulk degrees of freedom. Then, because this is a toy model, our boundary is no longer at infinity. At some finite radius, we just truncate our tessellation, and all of the remaining legs we just leave dangling and associate those with our boundary degrees of freedom. In this way, we've built some tensor network map that takes us from bulk to boundary. So we could plug in some bulk operator acting on our bulk degrees of freedom to this tensor network map and get some boundary operator acting now on our boundary degrees of freedom. And obviously, the tessellation we choose and the tensor we choose is going to impact whether this map has connections to ADS-CFT and looks like real holography or it just gives us junk. But happily, there's been lots of work on this before. Okay, so some of the problems, though. So the first models mapped a local bulk Hamiltonian to a non-local boundary Hamiltonian. This means if you start with some perturbation that acts locally on the bulk and you push it out with the tensor network, you end up with something that acts on like a constant fraction of the boundary globally. As this boundary Hamiltonian then doesn't respect the boundary metric, we can't use Lie-Robinson velocities to argue we have these nice light cones. However, potentially all is not lost. We could think about a more relaxed version of causality called butterfly velocities, where we just think about the propagation of information when restricted to the code space of the boundary. And this has been thought about in these tensor network models, where you consider a perturbation in the bulk and some connected region of the boundary, and you can sort of track it through and see how it spreads on the boundary. However, here you can see that, for example, you could think about a bulk particle moving through, like falling into the bulk. And when you track this using butterfly velocities with the original tensor network methods, you end up seeing that the boundary perturbation is constrained to some cone, but it's spreading exponentially on the boundary. Okay, so some work has already been done into trying to build better tensor network models, which maybe keep some sort of locality on the boundary. And this is where Hamiltonian simulation comes in. So this is the idea that you could take some Hamiltonian H that lives on some complex interaction graph, maybe it has interesting physics, and build some Hamiltonian H tilde that lives on some simpler graph, such that H tilde approximately has the same physics of H. And by having the same physics, it's been shown that if you have a valid Hamiltonian simulation, then the two Hamiltonians will approximately have the same measurement outcomes, the same thermal properties, and the same time dynamics, which is happily what we need if we're thinking about these non-local attacks on position-based cryptography. And there's lots of techniques from Hamiltonian complexity literature which help you constructively do this. So you add in extra qubits and you increase the interaction strength, and you can simplify your graph in some way such that you still maintain lots of aspects of the physics approximately. So this has been done in previous tensor network models where you start with your non-local global boundary Hamiltonian, you get straight from your tensor network, you apply some simulation techniques, and you end up with some boundary Hamiltonian that is now approximately the same as your non-local one, but now it acts locally. So we sort of regained a meaningful concept of boundary distance since we now have a local boundary Hamiltonian that's dual to our bulk. However, the penalty of doing this is we've increased the interaction strengths. And this means that information on the boundary theory, if we look at Lie-Robinson velocities, is just way too fast. And this is sort of not what we wanted. So we can think about particles moving through the bulk and around the boundary, and those two pictures should be dual, so it should arrive at the same time on the other side. But our boundary Hamiltonian is going to propagate it way too fast. So there's this inconsistency in causality there. And then if we look at this and think about whether we can build a attack on position-based cryptography from the ideas mentioned earlier, we have straight light cones, but they're just too flat. So there's this big region in the center of the boundary where all of the inputs could be brought together and the unitary could be implemented locally. So we have some dual boundary protocol, but it's not giving us an attack necessarily. And we can't really prove that it is because there's this whole region where it could be doing anything it wants. Okay, so this leads us to this ingredient that we noticed that maybe we thought could help us recover some more of this boundary causality. So if you look at the ADS metric, the hyperbolic tessellation that we've used is what's encoding this spatial curvature that we have in ADS. But you can also see that there's some time dilation going on here in the metric. So if we consider some stationary observer that's deep in the bulk and a stationary observer that's close to the conformal boundary, then the coordinate times of those two observers differs by this exponential factor. Or the observer in the bulk coordinate time is exponentially dilated with respect to the boundary. And since we've just taken a spatial slice and mapped the Hamiltonian and then time evolved, we sort of neglected this whole idea. So in order to take this idea from ADS and put it into our model, we need to put it in by hand. So this is what we did, and we went through carefully translating these model parameters and got this relationship between the time at the truncated boundary and the time at some tensor layer x from the middle. And you can see it's related by this, again, exponential factor where tau is some proxy for curvature in our model. It's like tau to the r minus x. And we insert this time dilation in by hand to the tensor network models. And we have the freedom to do this in the Hamiltonian interaction strengths. So we basically just make the bulk Hamiltonian such that the Hamiltonian interaction strengths decay exponentially as you move into the bulk. And happily, this gave us a few things. So it matched up the particle traveling across the bulk and around the boundary. These things now happen in the same time. And they also straightened out our butterfly velocities. So even without Hamiltonian simulation, if we just look at these, look at the butterfly velocities of something moving on a connected portion of the boundary, then they now move in straight light cones, which is nice. And it's nice that this correction came from inspiration from the ADS. Okay, so now we've recovered some causal features, like more than we had before. Is this enough to implement a position-based attack and show that position-based cryptography is insecure? The way we would do this is starting with the state that's on that the two referees give us. Propagating in is just done by local swaps, and we can use the boundary butterfly velocities to ensure that all of this on the boundary is constrained to these nice little causal diamonds. However, in the center where we want to simulate the unitary, in the bulk we're doing the local unitary that's generated by some Hamiltonian. And this is where we need to push it to disconnected regions of the boundary. So here we can't use butterfly velocity argument, since we need it to be a tensor product over these two regions to connect to there being like two, to keep the boundary geometry working. So we need some good simulation that means that when we push this out to these two disconnected regions, we can imagine there's still an Alice and Bob attacker going on doing things independently. And then once we've done this step using Hamiltonian simulation, we can go back to using butterfly velocities to push it out to the end, and we get these, we can say that we've done the boundary protocol in these nice light cones, and since the tensor network obeys Ryo-Takanaki, we still have the same entanglement bound. So this is, again, a linear entanglement attack. So as I sort of spoiled earlier, we don't quite have this last piece. So we don't have a constructive example of these good simulators that we need to do this central part. But what this does give us is a nice connection between two quantum information topics. So if position-based cryptography implementing a general unitary on n qubits is secure against non-local attack with linear entanglement, this implies fundamental lower bounds on the resources required for one Hamiltonian to simulate another. And this goes by a contrapositive argument. So if you give me that good general simulator, I can just plug it into the protocol to get a constructive non-local attack that uses linear entanglement and is going to break all of my position-based cryptography. And just to point out, while this is obviously heavily inspired by holography and ADS-EFT, because we've done it in a tensor network model, we've got rid of all those assumptions that, I don't know, things about quantum gravity or access to some holographic dictionary. This is really a real rigorous attack that we could feasibly imagine building. Okay, so, and what's nice about this is the limitations that we get on simulation from this argument have a precise scaling. So we can show that in order to maintain this, the causal structure on the boundary that we need, it implies that there's a simulated Hamiltonian that's too local with interaction strengths scaling like poly n to the a over epsilon to the b, where n again is the size of my state in my non-local computation, and epsilon is the error in my simulation, where a plus b is less than 1. So this is a nice form, and when you compare it to some of the other known results about no-goes for Hamiltonian simulation, like for example, we know that from this paper from Aronov that the strengths have to depend somehow on n and epsilon, but we don't have too many explicit examples of what this scaling should look like. So this implication gives us that if we can prove position-based cryptography being secured by other means, I mentioned there's some unrelated to holography work that works on this. This implication will give more precise lower bounds on simulation. While I've stated this main theorem in a general sense, there is an immediate corollary that brings forward this link between cryptography and complexity. So you can consider some class of position-based cryptography protocols that implement unitaries, local unitaries that are generated by some class of Hamiltonians. And if those protocols are secure, then this would imply that those Hamiltonians are hard to simulate. A nice example of this is there are lots of non-trivial protocols that are generated where the unitary is generated by k local Hamiltonians. This gives us a k-sparse boundary Hamiltonian, and this result would tell us that simulating k-sparse Hamiltonians are hard. And again, by hard, it's really a precise statement that simulators for k-sparse Hamiltonians cannot exist with interaction strength scaling like this poly n over a to epsilon over b. And a question of how tight this is, in this specific case of sparse Hamiltonians, when we were investigating this, we were really trying to fill this gap in this proof to, well, see what was going wrong. And in this paper, we construct new universal sparse Hamiltonian simulators that were exponentially better than the existing methods and achieve a plus b equals 1.5. So it's frustratingly close. But it's nice now that we have this implication, since maybe if by other means we can show that position-based cryptography is secure, then maybe there's some fundamental reason why we can only get to 1.5 and 1 is really a hard limit. Or the other way, if we can boost this 1.5 to 1, then we'll be able to plug it into the attack and be able to show that it's insecure, which I think potentially is the less likely route. So just to summarize, we introduced this new ingredient, this inserting by hand the time dilation from the ADS metric into tensor network models, and this gave us some consistent causality features on the boundary. And while this wasn't enough to make constructive attacks on position-based cryptography, it did allow us to make this implication, which means that further work on either direction can have nice implications in in the other field. So I'll leave you with some open questions, and thank you for your attention.
Thank you. All right. Any questions? Please use the mics if you have any.
Thank you for the talk. I'm a little bit, maybe you can help me explain a little bit what you say in statement 2. You say you need a protocol secure against implementing a general unitary on n qubits, secure against n entanglement. Sorry, you say n qubits and needs to be secure against O(n) pre-shared entanglement.
Yeah.
But I think that's like almost everything, right? I mean, oh,
Yeah, so sorry, there is a constant there that's greater than 1.
okay, yeah. And how does it work? For example, if you have 1 qubit and n bits, then we have protocols like that are secure against O(n) entanglement. Like, is there any difference between qubits and bits in this whole picture, or is a bit then also like you have to see it as a qubit?
I think you have to see it as a qubit.
We have time for more questions. Okay, I guess it was a very clear talk. Thank you.